Hello, everybody. Very good evening to all of you. Let's wait for some time to see if somebody joins. I can see so many people here. Okay, so let's start with the assignment problems from last week, and then we'll continue to actually discuss some concepts and problems out of electromachining process, electrochemical machining process, which is your current week content. So starting with previous week assignment questions. So yeah, uh, you can see on the screen your previous week assignment questions. We'll first discuss these questions in some detail and get your doubts cleared if you have any. And then consequently, we'll be uh, just looking at some of the concepts and problems from your current week content, that is your electrochemical machining process. That said, I hope all of you must have gone through all the videos of the current week, and then if you have any doubts, you can shoot it anytime. So starting with previous week assignment questions, the first question said that the most important function of a dielectric medium in EDM. So we had discussed that last problem solving session. So the most important function of dielectric medium is to flush away the debris. Okay. Out of these four questions, these four options. So to take away the debris with it has to be your most important function. Okay. Then the next question said dash flow is designed to carry away dash and a machine at required dash. So if you look at the options, then if you take up the first option, then electrolyte, of course, electrolyte is a fluid which flows. So electrode is not the one. So option B and D gets cancelled instantaneously, and then you have option A and C. Okay, so if you look at the options, then what is electrolyte flow does? What is it purposed for? Okay, so it doesn't take over the machining products. If it takes over the machining products, the question is from uh, ECM, I think, electrochemical machining actually, and then it takes over the heat. Okay? It doesn't take over the machining products, and then machine at a required feed rate. Okay, not RPM. There is no rotary motion in this process. Okay, so I hope that is clear. And if it is so, then the third question says which of the following is true? So this is the common question, that life of an ECG grinding wheel. Okay, what is the thing about it? The ECG grinding wheel is generally much larger in size than a conventional grinding wheel. Okay, so electrochemical grinding, and generally it is in the order of around 8 to 10 times more than that of conventional grinding wheel. Okay, so option B has to be the correct option here. Okay, so then it says that for maximum power delivery using resistance, capacitance, relaxation circuit in EDM. Okay, so this was derived in detail. Yeah, so of course, it's a discharge voltage. We had already discussed that in the previous session, and it is generally 72% of your applied voltage every knot. Or supply voltage. So option B goes to be the correct one here. And then you have hydraulic force in electrochemical drilling. So hydraulic force with electrochemical drilling operation, in the course of electrochemical drilling operation, hydraulic force generally increases. Okay, and then have in EDM, the workpiece has to be conductive. Otherwise, how can an electrodischarge machining take place, right? And there will not be any flow of ions and electrons, and there will not be formation of an avalanche of ions. Okay, we discussed the basic principle of EDM last session at the very starting time. So the workpiece has to have conductivity, okay, for EDM process to happen. So this is of material chemical dissolution. Now, of course, electrochemical dissolution takes over the maximum amount of material. That is the basic principle of the process. So generally 90%, around 90 or more than that, 90% or more of the material removal takes place due to electrochemical dissolution process. And the remaining generally happens due to mechanical abrasive action on the work surface. Okay. Now, in EDM, the primary function of electrolyte, of course, part of it was discussed in the first question. So the primary functions, yeah. So carrying over the heat or waste product, already we discussed above, and sustaining the required electrochemical reactions. Yeah, so both are important. So option A and B has to be the correct one only. Then which of the following material can be machined using EDM? Of course, it should be a conductive material. And out of the four options, you can see iron is the only one which can fit into the required answer. Okay. Now, this is a numerical problem. It's a simple numerical problem. You have to find out the cycle time first. The question says that the applied voltage is 240 volts and your discharge voltage is 180 volts. Then you have to find out the cycle time when the resistance is 10 milliohms, okay, and capacitance is 10 millifarads in the circuit. Now, using the data and just plug into the equation for cycle time. This had been derived earlier. So it is RC natural log of your supply voltage divided by the difference of your supply voltage and discharge voltage. Okay. Now you just plug in the values of resistance, capacitance, and supply and discharge voltage to get the cycle time is 0.139 milliseconds. Yeah, and this is a pretty simple problem. I hope all these questions you have been able to do. And if you have any doubt, you can kindly ask. Okay, so if you have no doubts, then we'll proceed to our mm, discussion about some of the topics out of electrochemical machining process and the related problems. Okay. So we will just jump to the basic principle of the same process. So there is a cathode, there is an anode, and there is an electrolyte flow in between them. Okay. Generally, the tool is made the cathode, and the working material considered for machining is kept as the anode. Okay. Now, what's the basic logic behind the same process? There should be machining of the workpiece, and the tool should remain intact, right? That is the ideal process definition. Now, for that to happen, the process follows as when you apply a voltage difference, and then there are two reactions happening at the cathode and the anode. Okay, so at anode, what happens is the iron, which is the electrode material, it loses two electrons and turns to a positive ion Fe2 plus. Okay, now at cathode, what happens? The water takes up these two electrons and evolves into hydrogen gas and two negatively charged hydroxyl ions. Okay, now these hydroxyl ions actually start traveling towards the anode, and the positively charged ions just start traveling towards the cathode. Okay. Now, once that does, your negatively charged hydroxyl ion just react with Fe2 plus. Okay, you can see here to give rise to an insoluble precipitate called ferrous oxide, FeOH2. Okay, and that way at your anode there are continuous dissolution of iron taking place, and precipitates getting formed in the form of ferrous oxide FeOH2. Okay, whereas these hydroxyl ions then just negatively charged hydroxyl ions just give rise to hydrogen bubble formation. Okay, so that is the process, and in that way your cathode remains intact and there is continuous dissolution of your anode. Okay, that is the basic principle of your ECM process. Now the question arises, what happens to this insoluble precipitate? Should that be present there? And what happens if it starts accumulating? Okay, accumulation of precipitate should not be there. For that thing, and that is one of the function of the electrolyte which is flowing. So your next question that comes up is why is this electrolyte flow necessary in this ECM process? Okay. So this is one reason which we just discussed about the precipitation which happens. Okay, the precipitate formed must be removed away. Okay, isn't it? So that is one of the primary work of the electrolyte which is there. Now, there are three other reasons which are to avoid the ionic concentration. Okay, so if the ions keep on concentrating at one point and having a lower concentration at an other point, so that means that there will be a differential material removal and an uniform shape of the machined material can't be achieved, right? So the ionic concentration should not be there, and this is where the electrolyte flow is necessary. Okay, and then avoid deposition on tool. Yeah, that should not happen. All the precipitate should go to the solution. This is another reason, and then overheating of the electrode, of course, when when a voltage difference is applied, the heating happens. We'll actually discussing this heating phenomenon in the upcoming slides. So electrode overheating should also be avoided. and electrolyte flow just facilitates that. Okay. Now, after that, I hope this part is clear to you. Okay, then we'll move to our next content, which is directly comes up in relation to our earlier content, the temperature and pressure during the same process. What is the heat generation? How much is the heat generation? Okay. How much is the rise in the temperature during the ECM process? So let us assume that all the heat generated by the flow of the electric current should remain in the electrolyte only. Okay, I mean, let's neglect the heat conduction through the electrodes for simplicity. Okay, now this figure here shows your electrolyte flow. Okay, suppose the electrolyte comes in from here. Okay, and suppose let's assume we have a this type of path. Okay, so the electrolyte comes in from here, moves out from here, and this is your equilibrium gap y. Okay, this y, and then current flow takes place from the above. Okay, here suppose is your tool, and below that happens to be your work. Now temperature initially let be theta naught, and finally temperature rises to become theta naught plus an incremental temperature rise, which is del theta at the outlet. Okay. Now we have considered, okay, so this is your dx portion. Okay, so this dx, and suppose this differential element to take at a distance of x from initial position. Okay, now considering all these factors, let's go and find out the amount of heat carried out by the electrolyte. So this is a basic heat storage formula. You know that if you take the heat flow per unit area, that is your mass flow rate multiplied by your heat capacity of your electrolyte and the temperature rise del theta. Okay. Now, how do you find the mass flow rate? Okay, so mass flow rate can be found out as rho Q. Okay, Q is the discharge rate, okay, or volume flow rate, or you can say it is rho area into velocity, okay, of the electrolyte. So these are for the electrolytes. Now here, if you plug in the values, let's take that depth is 1. Okay, so you have y as your equilibrium gap, or the gap between the tool and your work at equilibrium. Okay, so this part be your y. This is the direction of tool motion. So we have taken the depth as 1, and so the area becomes y into 1. And this is your velocity, this is your density of the electrolyte, capacity of the electrolyte, and the temperature rise and del theta. So the power generated then is given by I square R. I is your current, and then it follows that J is your current density, okay, which is current per unit area. So then it follows that when you replace I as in terms of J, so I is given by your J into area, okay. So your area is again dx, this area, okay, this area. So of course it is dx multiplied by your unit depth 1. So that follows your total current, your current density multiplied by area, square of that multiplied by your resistance R. Okay. Now you do replace R in terms of your R is given by density times okay, length by area, okay. And then this is your reciprocal of your conductivity K L by area. So just plug in these values to find 1 by K. Your length is your equilibrium gap Y, and your area is dx multiplied by 1. We have taken unit depth, as I have mentioned multiple times. So if you just resolve this, you get it as J square of dx divided by K conductivity into equilibrium gap Y. J is your current density. So that now you just equate the two heat equations, your total amount of heat carried away and the total amount of heat generated due to the give applied potential, okay, or the heat generation due to the resistor, okay. It is I square R. So just equate these two to find out your del theta as your J square dx divided by conductivity times velocity VE, okay, your density of electrolyte material rho E, and your heat capacity CE. So yeah, so this gives your temperature rise equation. Now obviously your conductivity not is not independent of your temperature variations. So conductivity should also vary in terms of the incremental rise in temperature. So conductivity equation again follows as K multiplied by your K naught multiplied by your 1 plus alpha, which is diffusivity, thermal diffusivity, and then theta minus theta naught, okay. So given that, you just integrate both sides of this equation to find out your velocity of electrolyte flow, okay. That is an important parameter to know. You just integrate, dx becomes your total length L, L be the total length of flow, okay, L. And once you do that, you find out your velocity of the electrolyte flow as J square L divided by your K naught into del theta plus alpha into del theta square by 2 multiplied by your density and heat capacity of the electrolyte. Now, another important parameter is the pressure required to maintain this velocity, okay. Now, assuming a turbulent flow, I will not go to the derivation of these. The pressure required happens to be this one, okay. Now, here you have two parts. The first part belongs to the pressure required to overcome viscous friction between the plate and electrolyte, okay. And then this second portion, rho v square by 2, is the pressure required to overcome the inertia, with inertia, okay. However, this part is very less. Okay? This part happens to be very low because of the size effects and all. It's a minimal size, and the inertial are quite low. Inertia values are quite low, and hence the pressure required is minimal in comparison to the pressure required to overcome the viscous friction between the plate and the electrolyte. Okay? So the first part plays the pivotal role and the total pressure required to maintain the required electrolyte velocity. So I hope this part is clear to you all. So let's proceed to our next content. Here comes a numerical to solve, and of course, it is related to the current topic, which is your temperature rise and velocity and of the electrolyte tau and the pressure required to maintain that velocity. You just derived everything. You take note of those concepts and just try to solve this problem. So I'll read out this problem for you. It says that in an ECM process, in an ECM operation, what happens is that square-faced copper tool is used and a brine is used as an electrolyte. Now both are having a flat surface and a feed rate of 2 millimeters per minute is used. Okay. The DC voltage is used of 10 volt and the over voltage is 1.5 volts. The dimension of the tool face is 25.4 millimeter. It is a square tool, so you can just take it. The area is 25.4 cross 25.4, and the boiling temperature of the electrolyte is 95 degrees centigrade. Okay. Now you have to find out the total force acting on the tool. So you can just follow the entire process to find out the total pressure required, and then from the pressure you multiply the exposed area to find out the total force. Okay? So these are your given data for the electrolyte and your initial temperature. So you use this data to find out what should be the total force acting on the tool. So give it a try, and then we'll try to solve it interactively. Okay. So I hope you have tried your bit on this question, and if so, let's now discuss the solution. So this question, you have to find out the total force. Okay, so if we go with the actual flow, now it is an same operation on iron workpiece. A copper tool, which is a square flat surface, is used, and brine is used in electrolyte. Over voltage is 1.5 volts, and your applied voltage is uh, 10 volts. Okay, so you have that area of the tool is 25.4 square mm square, and boiling temperature is 95 degrees centigrade. Now the viscosity of the given electrolyte is 0.876 into 10 to the power minus 3 kg per meter seconds, and your density of the electrolyte is 1.088 grams per centimeter cube, right? Yeah, it is given here. And then your heat capacity, heat storage capacity of your electrolyte is 0.997. Conductivity is 0.2 per ohm centimeters, and the ambient temperature is 35 degrees centigrade. Okay. So given all these things, you just plug in to your values, plug in your values. So if you are not aware of these formulations, no worries will actually be coming to such to derivation of these equilibrium gaps later on in today's session and in the upcoming slides. So for now, those who are not aware of these formulations, these have been actually taught to you in the current week. I should know. And if you're not, then I'll discuss it in the upcoming slide. So your equilibrium graph is given by your lambda by feed. F lambda is your constant, and then Ka V minus del V. Del V is your over voltage divided by your density atomic weight, then your coulombs number 96500, and F is a feed rate. Okay, so you just plug in the given values. Everything has been given to you. Okay, so Z has been, this is for iron, right? So for iron, you have to take care of your atomic weight actually. So for iron, your atomic weight A is nothing but 55.85 grams. Okay, if you don't know, atomic weight for iron is 55.85 grams. Okay, and your valency Z is 2. You just plug in the values F, 96500 coulombs, and feed rate is given to you as 2 millimeters per minute. Okay, the feed rate is also given as 2 millimeters per minute. Then J is your current density, which you find as current per unit area, okay, which is conductivity multiplied by your voltage minus over voltage divided by your equilibrium gap. J comes out to be 85 amps per centimeter square. And then you find out your velocity, okay, which we just derived earlier. It is J square L divided by your K naught del theta rho E into rho is your density of electrolyte and capacity, heat storage capacity of your electrolyte. Okay, just plug in the values and find out the velocities, 1400 centimeter per second approximately. Okay. Now, once you have the velocity, then you can go on to find the pressure required to maintain that velocity. Okay, the formula we just gave you earlier, 0.3164 density into velocity square into length divided by 4 of equilibrium graph. This is Reynolds number, characteristic Reynolds number for the particular material used, and then particular flow raised to the power 0.25. And this you can neglect because of very minimal inertial effects. Okay, So just plug in the values. You're using the first term, you get almost equal to 238 kilonewton per meter square of pressure. Okay. Uh, and using this pressure value, just multiply with the exposed area, to the square tool, it is of 2.54 mm square. Okay. So just plug in the values to find almost equal to 79 Newton of force required to maintain the electrolyte at the required velocity. Okay. So given that this completes this problem, I hope it is clear to you all. So assuming you don't have any doubts, we'll proceed to our next topic for today's session, and that is with regard to some of the problems about your interelectrode gaps and the way the equilibrium is attained between your work and tool during electrochemical machining process. Okay, so these are pretty simple problems, and however, before those problems, as we discussed earlier, for the people among you who are not aware of these formulations, okay, so let us first take up one question that regard of how do you come up to the equilibrium gap actually. So in terms of the question, it is that in the electrochemical machining process, you use the fundamental Faraday's principles of electrolysis and show that after a particular time t, the interelectrode gap varies through a parabolic profile. Okay, assuming that no tool feed is given. Okay? Generally, don't give any feed to the tool, and when an equilibrium gap is maintained. Okay, so just we have to start with current density, which we just discussed earlier. It is your current per unit area, J. Okay. Now, you know that current is voltage divided by your R, where V is your supplied voltage and del V is your over voltage. Okay, so the net available voltage is your V minus del V. You divide it by resistance R and take out 1 by A area as common. So if you take this depth of the work and tool as 1 for simplicity, you take a unit depth, then we can see that this area becomes the inter-electrode gap Y multiplied by the unit depth 1. Okay, so just take up an area like that, okay, where this is your Y and this depth is your unit depth assumed in this problem. Okay. Now R can be replaced as 1 by conductivity into L by A, which we just have discussed earlier. And this comes down to K multiplied by V minus del V by inter-electrode gap Y. Okay. Now you have to find that how this Y is varying. Okay. Just the tool continues to move. Actually, the work and tool is always having relative motion between them, right? So how to check how your Y varies, you should check what is the rate of motion between the two tool and the work. Okay? So your rate of change in gap can be found out by the actual MRR which is happening out of the workpiece and subtracting the actual feed velocity of the electrode. Okay? So that gives you relative motion between your work and tool, and that, in other words, gives the rate of change of your inter-electrode gap Y, right? So dy dt, the rate of change of Y with respect to time, is your the difference between the MRR and the feed velocity of the work towards the electrode. Okay? Now, sorry. What is the MRR in case of AODCM process? Hope you have gone through the videos of the current week lectures, then you must know that the MRR is given as through this formula, which is A, where A is your atomic weight, J is your density, current density, rho is your density, Z is your atomic number, and F is your Coulomb's constant, okay? And a small f be your feed rate. So given that, you just plug in the values of J, which we have just found in the earlier slide, and you see that dy dt comes down to lambda by y minus f. Okay, so what is lambda here? Lambda is just assumed, it's a dimensionless constant and has been assumed as v minus Ka V minus del B y rho ZF. Okay. So this term has been assumed lambda for simplicity. Then your rate of change of inter-electrode gap can be shown as lambda by y minus your feed rate F. Okay. Now we can have two particular cases. So the first case is when the feed rate is 0. We don't apply any external feed rate to the work or tool. And then from this equation, you can see that this F becomes 0. Now, dy dt becomes to lambda by y, and you just do simple integration showing that y happens to be your actually y squared. After your integration, y squared should come out as your y naught squared plus twice of lambda t. That now, when you just take out the root, then this equation is followed. In other words, your y square is varying, your inter-electrode gap is varying as square of y, right? So it is a parabolic variation with y naught as your initial gap, and then it varies as y naught square plus twice of lambda t. It is a parabolic variation, and that is what has been asked in your question, right? So this case answers the question asked, and then this is another case when f can be constant. Okay? So if f is constant, then we know that lambda is also a constant term, and overall you see that the rate of change of y with respect to time should become 0. So just equating that, you see that y equilibrium graph happens to be lambda by f. You know the value of lambda. So this was the value that should be actually that was used here in the earlier question. So I hope that clears your doubts if somebody was not aware of this formulation. Now, given that, uh, we'll move to two problems related to this topic. Okay. Now, so the first one is that in an ECM operation with flat surfaces, a 10-volt DC supply is being used, and the conductivity of the electrolyte is 0.1 per ohm centimeters, and a feed rate of 1 per minute is used. Okay. Now the workpiece is pure iron, and the values has been given to you for your reference. You just have to calculate the equilibrium there. So this is a simple solution to this problem. Your supplied voltage was given as 10 volts. Over voltage is 1.5 volts. Conductivity of iron, it is, sorry, of the electrolyte, it was given as 0.2 per ohm centimeters. Feed rate was 1 per minute, and this atomic weight and valency and density for iron, right? Now you just plug in to these plug in the values to this particular equation which you just derived in the earlier slides, and then you come up to the equilibrium gap as 0.04 centimeters. So this is a simple formula based question. If you understand this, then we'll take up a question from, and actually we'll first derive something related to tool geometry. You know that uh, actual tool geometry is necessary for accurate machining of an workpiece. And there is a method to theoretically derive the tool geometry based upon the desired work geometry you need after your machining complex. Okay. So just take a note of this type of derivations. We'll just come up to the lengthier derivation of a tool geometry theoretically in the upcoming slides. So this is one more question, basically almost similar to the earlier one. Here it says that the surface irregularities of electrodes are 5 and 8 microns given to you. Okay. Now, this is where the simple logic you have to apply. By surface irregularities, actually it has been meant that the heights and peaks of the asperities that can be formed on the surface of the workpiece during the machining process. Okay? Now, you know that surface finish is not a very good, and there are certain factors which can affect surface finish during the process. Now, so suppose there was surface deterioration and peaks and valleys has been formed during the process, and which are of dimensions 5 and 8 microns respectively. Okay? Given that, you just have to find out the largest possible feed rate, okay? And assume the all the parameters similar to the earlier problems. So suppose this was your work profile and this was your tool profile. Okay. So the peaks has been given as 8 microns and the valleys as 5 microns. So this be your work and this be your tool. So what follows is the total electrode gap has now increased because of these asperities formed, and now the total electrode gap becomes 8 plus 5, and that is 13 microns, which has been increased out of the nominal gap. So this be your nominal gap or equilibrium gap, you can say. Now 13 microns becomes your increased gap, and for that increased gap, what should be the largest possible feed rate? So just plugging the value of equilibrium gap as 13 here, and just use this formula for equilibrium gap and plug in the values to find out the feed rate. Okay? And that answers your question. Now, if you have got that, we'll proceed to actual theoretical tool geometry determination. I will take you through the 2D tool geometry determination, and you can also do that for a 3D tool. I'll just give the hints, and you can do that in the 3D one. And if you face any doubts or any problems, then you can discuss in the next session. So this session will just take care of the 2D shape tool. Okay. So let's suppose we have a work surface of any profile, which is here assumed to be a curved profile like that. And then we have to design a tool which should almost exactly resemble the work profile that we like to generate. Now let's PW be a point on the work and PT be a point on the tool with coordinates, respective coordinates of X and Y. And let F be the feed force on the tool, on the work towards the tool. Okay. Let Y be a function of X as shown. And suppose the total perpendicular gap between the work and the tool is given by this line. And Q or GE, GE in this case, yeah, GE be your equilibrium gap. Okay. So it says GE is your equilibrium gap, the line represented by PWPT. And this is in turn given by YW minus YT. YW is your Y coordinate at PW, and YT is your Y coordinate and PT. So the total difference YW minus YT given by this perpendicular line. Okay, this is YW minus YT is nothing but your equilibrium gaps cosine component. Okay? So this is your theta, the angle between the equilibrium gap and the distance at any point of time t. So GE cos theta is given, gives this line YW minus YT, which has been shown here. From that, you can take out YT. You should remember that T superscripts are always for tool geometry, and W is for work geometry. Okay. So YT then follows as YW minus of this GE cos theta actually. So you know that from the earlier derivation we had, this is lambda by f if there is no angle variations, and it is lambda by f cos theta if the geometry is varying with angle with theta. Okay. Now, given that the cos theta component gets cut off from the numerator and the denominator, and you are just left with GE, which is nothing but lambda by f, and this is your lambda, which was derived earlier, and at the denominator you have the feed rate f. Okay. So this has been resolved to YW minus lambda by x. Similarly, you find the x component for the tool geometry as xw plus lambda by f tan theta, because this is sin theta and GE already has a cos theta at the denominator. So overall, you have the tool x coordinate or x component is xw plus lambda by f of tan theta. Okay. Now, where tan theta is your differential change in y component with respect to x component, or dy dx, the slope, okay, for the work geometry. Now, just replacing that in the above components, you have the y component of 2 less YW minus lambda by f, but you have a tan theta component in case of the x component of the tool. So the total x component for the tool becomes xw plus lambda by feed rate into tan theta, which is nothing but the slope of the work. That is T of YW by D of XW, right? Now proceeding, we had earlier considered YW to be a function of XW. XW is the X component of the work geometry. And YW you can replace as YT plus lambda by F, right? So just replace YW as YT plus lambda by F, and just replace the value of xw in terms of tool geometry. Okay, we're just taking up the value for YWs in terms of tool coordinates YT and XT. So this is what follows, and then we have just taken this lambda by a value to the right side, and you have this equation representing the tool geometry. So one thing you can see that still there are some values of the work geometry left. Okay. Now this is derivative of y component of the work. So let us suppose, okay, so this is one assumed work geometry which can vary as per the requirements in various situations. In this case, you have the y component of the work. Let's suppose it is some constant a plus b of x plus c of x square. Okay, and let this be a polynomial of degree 2, and then we just replace that in terms of derivative with respect to x. Okay, that becomes b plus twice of x, and the constant c gets out. Okay. Now you replace again xw in terms of tool geometry xt, and just replace this d phi dx value, and you can find out the total d phi dx after resolving the RHS and the LHS part. You find that the d phi dx comes down to p plus 2c xt by 1 plus 2c lambda by f. All these things are in terms of tool coordinates xt and yt now. So just take this value back there, and you can see that the total y component of the tool can now be found out with all the x coordinates of the tool only. Okay? So this is a way to derive the tool geometry when a particular work geometry is given, and then we can this is a generalized expression in case of 2D geometries. So we can also go to 3D geometries, and this slide just gives you a hint about that. If you understand these things, then you can try deriving the geometry for the tool in 3D when your work geometry is given to you. Okay. If you find any doubts, you can take up the derivation in the next class. Till then, you just try it at home. Okay. So I hope there are no doubts regarding this derivation. So let's take up a problem uh, regarding this current topic. We have to find out the tool surface geometry when the work geometry is given to you as 10 plus 0.3 of x minus 0.05 of x squared. Okay, then you can use this data to find out the equation for tool surface geometry. Okay, so let's straightforward go to the solution. You have a workpiece geometry given as 10 plus 0.3 x minus 0.05 of x squared. The voltage is supplied voltage is 15 volts and over voltage is 0.67 volt. So the net voltage difference becomes 15 minus of 0.67. Then your feed rate in mm per minute is given as 0.75. You convert it to seconds in centimeter per seconds because you have to maintain unit uniformity throughout the problem. And you find that the lambda value comes out to 2.11 into 10 to the power minus 4 centimeter square per second. Okay. Now you just find out the value of the ratio of lambda to feed rate and plug in the value just to the tool geometry equation that we have derived earlier. Okay. You just plug in, this is for work geometry, right? You have been given the work geometry equation. Just so this is xw, and this you can take as yw. So you just replace the xw's in terms of what we found earlier. Okay. This equation, okay, xt minus lambda by f of this. Okay. Just plug in these values here, and you can simply get the expression for your tool geometry y in terms of x. Okay. So this is how such type of problems needs to be solved, and then this MRR concept in ECM process. Okay. So these are simple demonstrations of how you get down to the expression for your total net material flow rate, material removal rate in ECM. That is just you take note of this gram equivalent weight of metal. Okay, so A is your atomic weight. When you divide that by the valence Z, that is called as your gram equivalent weight of the metal. Okay, and then you are acquainted with the Faraday's law, which says the mass flow is actually proportional to the current and the time for which the current is supplied, and the gram equivalent weight A by Z of the metal, and then your F, which is Coulomb's constant. Okay. Now you just plug in the values, and you find that you take the time to the left, and you find that the mass flow rate becomes I into epsilon by F. Okay, Faraday's constant, which is 96500 coulombs. And then if you know the mass flow rate, you just have to divide it by the density to find the MRR, okay, volume flow rate. So even that for an alloy structure, you can find out the total flow MRR. Okay. And just you have to find out the equivalent density given by this equation and plug in the value to the just you have to use equivalent density in case of density. Okay. Also plug in the values and take the equivalent weight. So that way you can find out the total MRR for alloy materials also. Okay. Now using this concept, just let me take you through a problem corresponding to the MRR in case of PCM processes. So suppose you have been given a mnemonic alloy of which these are your components, okay, with the maximum of nickel. For mnemonic alloys, we have a highest percentage of nickel with other substitutes or components in minor amounts. So you have been given with this table, and which you have the total atomic weight for all the components, the valency of dissolution, and the densities. So you take care of these values and find out the net or overall density of the alloy and the overall gram equivalent weight, and just plug in to the equation for MRR to get the desired answer. Okay. So you can see that the overall density can be found out in this way. You xi is just to enumerate, is an enumeration variable. It takes you through all the components of the particular alloy. In this case, whatever you are having as nickel, Gr, Fe, titanium, silicon, manganese, copper, whatever you are given, you just take the values from this table, the fraction of the corresponding components and the density of the corresponding components from here, and take out the equivalent density of it. Once you find this, you just plug in here where Zi is the individual, Zi stands for the individual valencies, Xi for the individual fractions, and Ai for the individual atomic weights. Okay. You plug in these values here and find the total summation of that, and you can find the MRR as 0.35 into 10 to the power minus 4 centimeter cube per second amperes. Okay. Now, from the derivation earlier, you have seen that the Q is in per unit area. Okay. So, and it is for 1 unit of electric current. And here you have been asked to find out the data for a total current of 1000 amperes. Okay. So you just multiply the net MRR with the given amperes, and you can find it in terms of seconds, and you multiply it with 60 to find out in terms of minutes, the centimeter cube per minute. So this type of problems were also solved in the class and are very much probable exams. So I hope you have a clear concept of these problems. The only difference in case of alloy is you have to find out the equivalent densities and the equivalent gram atomic weights. Okay. So if that is clear, then we'll probably move to the last topic of today's session, and it actually relates to the factors which affects the surface finish in ECM process. So probably there are multiple reasons, out of which 4 particular factors are the more influential ones, and we'll start with selective dissolution. Now, what does that mean? So actually the surface of the particular work material you are using in case of alloys need not be super finished surface, and there can be several constituents. Suppose you are using an alloy material and you are having several constituents on that. Okay. Now the different constituents can have different electrode potentials also, and then depending upon that, suppose this A is one component, one constituent of the alloy, and B is another constituent. Okay. So A is having a potential of VDA, and B is having that of VDB. Okay. Now depending on the local constituent, what happens is since the whole anode surface is equipotential and the electrolyte potential varies across the gap. So this is how the electrode potential may vary across the gap. So the surface of B must this constituent B must project away from the surface of the constituent A. Okay, so that the electrolyte meets with the lower potential of A. Now, so there is a larger difference VDB than achieved. Okay, so A is at a lower potential, B is at a higher potential. So B must be removed so that the electrolyte meets with the lower potential, and hence a larger potential B has to be removed. Okay, so this way in steady state the work surface becomes uneven, and the smoothness happens to get lost. Okay? So this is one reason which affects one factor rather which affects the surface finish in the same process. And if you got it, then we move to the second important reason, which is called the sporadic breakdown of the anodic film. So this is probably related to your reduction or reducing potential between the tool and the electrolyte, tool and the work, as we are moving away from the tool location. Okay? So you can see that up to point P1, we have enough potential to make all the components dissolve into the electrolyte. Okay, but after P, the distance crosses a critical distance, suppose XC. Okay, so after this point, this critical distance, after crossing this critical distance, the potential between the electrolyte and the tool is doesn't happen to be enough to make all the phases dissolved. Okay, and that continues to further reduce up to this point P2, where there are very minimal number of active phases left on the surface of the work. And however, the electric field has now concentrated because relatively the electric field is much higher now in comparison to whatever number of active phases which are left on the work surface. Now, this results to sudden rapid breakdown of some of the components from the surface, and large peaks are formed. Okay, you can see here. And this actually is called a sporadic breakdown of the anodic film. You know, the work surface is happens to be the anode. So breakdown of this anodic surface or anodic film is termed as one of the important factors for surface finish deterioration in case of electrochemical machining process. Okay. So did you get this? Yeah. And then these two are the two more reasons of surface deterioration. First one is your flow separation and eddy formation. Okay, so because of the surface irregularities, okay, there can be on the anodic surface there can be separation of the electrolyte flow, okay, and eddy formation. Now as some portion of the electrolyte separates, okay, a larger it may take away a larger concentration of metal ion, and which can result in a higher concentration of metal ions building up in the electrolyte at some parts, and comparatively lower ones building up at some parts. Okay, so there can be concentration over potential in the eddies at some points of the electrolyte, and this can introduce a localized variation in the removal rates, right? So probably then this variation in the removal rates actually can lead to irregularities in the surface, and you may not have a uniform surface finish throughout the work. Okay. And the last one, and quite an important one, is your hydrogen gas evolution. You know that we just started with this basic concept of electrochemical machining, that your cathode surface remains untouched, I mean undeteriorated, and there is continuous dissolution from your anode surface, which is the tool. So what happens is that hydrogen bubbles are constantly generated at the cathode surface, and at the same time the iron or the metal of the anode continues to dissolve to the solution in the precipitate form, okay, which is again carried away by the electrolyte. However, at some points, this may happen that the hydrogen gases can be much higher than critical value, and this can lead to reduction in conductivity of the electrolyte. Okay, so these may actually lead to increase in the downstream. The concentration of hydrogen bubbles may increase in the downstream, and this can in turn lead to deterioration of your electrode surface. Okay? So these are the four major reasons for which the tool deterioration take place. Sorry, work deterioration take place, and that follows your actual tool design, which needs to be taken up. So that's how I think we can conclude today's session. And if you have any doubts, you can just shoot now. Yeah. A has a question here, which asks about why AC power is not used in ECM. So we have discussed it earlier also that the tool should not deteriorate. Okay, there should not be any deposition on the tool. There should not be any degradation of the tool. What we want is only above of the workpiece. Now, if we set an AC potential, then the alternating current would lead to damage or erosion or dissolution of the cathodic material, which is the tool in cyclic turns. And this is highly undesirable, right? So we always use the DC potential, and so that only the work material dissolutes into the electrolyte and not the tool material. Hope that is clear. Uh, Changing. So one question was that the answer we have just discussed about why an AC potential is not used. So we said that this may lead to cyclic deterioration of the tool also. Now, one question that has been shoot up is that not desirable for an alloy material. So whatever material you use, that is not going to change the potential you are using, right? So what material you are using is completely invariable to what potential you are using. Whatever potential you are using, continuously you are going to change the cycles, the positive, negative electrode are continuously going to change in a cyclic pattern. So what material is being used, an alloy or a pure metal, doesn't really matter. It will obviously get deteriorated. I hope that clears the question. Okay, guys, so let's call it a day, and we'll be meeting the next session. Just try the 3D tool geometry thing. If you have any doubts, you can take it up in the next session. Till then, goodbye.